All right, so we're going to look at telescoping series. So some of the prior knowledge you need for this is sequences and series, which we spoke about in lecture 3, and what's called partial fraction decomposition. And I'll put a link below to explain what that is and where it comes from, but we'll need to be able to do that for this. Should be a reasonably short video, but we're just going to talk about the key concepts of what is a telescoping series and then evaluating a telescoping series. So let's jump into it. The kinds of questions we might want to answer are something like this. And it looks pretty hairy to begin with, but we'll make some sense of it. So it says prove that 1 on k multiplied by k plus 2 equals a on k plus b on k plus 2. And use it to show that 1 on 1 times 3 plus 2, sorry, plus 1 on 2 times 4 plus dot 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 up to 1 on n times n plus 2 equals 3 quarters minus 1 on 2n plus 1 minus 1 on 2n plus 2. So it might not be immediately obvious why this even relates to this series at all. But let's just break it down part by part. This first part it's asking us to do is to find the values of a and b, such that we can break this fraction into partial fractions. So again, go back and watch the video on that about distinct linear factors when you're doing a partial fraction decomposition. But I think you would agree, I think it shouldn't be too tricky to say that on the right-hand side, if we just sort of cross multiply, so k multiplied by b gives us bk, and k plus 2 multiplied by a gives us ak plus 2a. And then collect the terms with k, so ak plus bk, take k out as a factor, and you'll be left with k multiplied by a plus b, and then you'll be left with 2a. And we know that the numerators must equal one another, so we know that 1 equals 2a plus k multiplied by a plus b. And so we know that this term has a variable k in it, but this 2a doesn't have a k in it. So we know that 1 equals 2a, and this other thing must equal 0. So we know that a is therefore 1/2 because 2a equals 1. So a equals 1/2. And if this whole right-hand side, sorry, not the right-hand side, but this second term here, if this equals 0, then b must be negative 1/2 because we know that a is positive 1/2. Okay, then what we can do is we can rewrite our fraction, right, as a partial fraction decomposition. So 1 on 2k minus 1 on 2 multiplied by k plus 2. Because remember, b was this, and b turned out to be negative 1/2, so it becomes minus 1 on 2 multiplied by k plus 2. And 1 on 2k is the first term there. Okay, what we're just going to do here is you'll notice we can take out 1/2 as a factor. So we just get 1/2 multiplied by 1 minus, sorry, 1 on k minus 1 on k plus 2. Okay, this next line is going to look very confusing, but we're going to break it down. So what we need to do is you need to show this. You need to show that this left-hand side here equals this right-hand side. So let's start with the left-hand side, and then let's just look at this first term to try and make some sense of it. It says 1 on 1 multiplied by 3. But we know that that's sort of this form, right? If this is the first term, then k or n, say n is 1. So it's 1 on 1 multiplied by 1 plus 2, which is 3. We know that this can be written as a fraction decomposition, exactly like this. So firstly, let me just point out we can take 1/2 out the very front, and then we're going to be left with 1 on k, which is 1 on 1, minus 1 on k plus 2, which is 1 on 3. So this first part here, 1 on 1 multiplied by 3, can be broken down into this. And remember, we've taken 1/2 out as the factor at the very front because it's going to be a factor of all of these terms. Okay, this second term here becomes this part here. 1 on 2 now minus 1 divided by 1/4 plus 1 on 3 minus 1/5 plus 1 on 4 minus 1/6 all the way up to, and this is where it gets confusing, we're going all the way up to n, right? We're going to the nth term. So let's start from the right-hand side here. We know, just sort of looking at this pattern, the first term in the brackets is 1 on n minus 1 on n plus 2. You'll notice that's sort of the pattern that's occurring here. If we were to take that to the second last term, well, this denominator of the second term in the brackets, this is n plus 2, so this one would be n plus 1. And similarly, the second last term in the first position in the brackets, if this is 1 on n, then the previous one would be 1 on n minus 1. And so now this is where we get the telescoping effect, which we haven't even really spoken about. But basically, a lot of these terms are going to cancel out and they're going to collapse just like a telescope does. This minus 1/3 will cancel with this positive 1/3. This negative 1/4 will cancel with this positive 1/4. And this 1 on 1 will actually be left and this 1 on 2 will be left. But I encourage you to continue the sequence on pen and paper or think about it. But this minus 1 on 5 would get cancelled with a positive 1 on 5 out to the right. Similarly, this negative 1 on 6 would cancel with a positive 1 on 6 further down. And so, following that same pattern, you can see that the two terms that are left at the start is 1 on 1 and 1 on 2, which is the first term in the first two brackets. Following this same pattern towards the end, you would actually get that the first two terms a bit tricky to explain, but I thought it'd be easier if I crossed them out. Basically, 1 on n minus 1 and 1 on n will cancel out with previous terms in the sequence, but you will be left with negative 1 on n plus 1 and negative 1 on n plus 2. And so these terms that have sort of crossed out are collapsing like a telescope, and then you're left with 1 on 2 multiplied by 1 on 1 plus 1 on 2 minus 1 on n plus 1 minus 1 on n plus 2. Expanding that 1/2 in, you get 3/4 minus 2 n plus 1 minus 1 on 2n plus 2, which is what we needed to show. So that's sort of the telescoping effect there. Let's now use that to evaluate an example. So yeah, what if we needed to evaluate 1 on 1 times 3 plus 1 on 2 times 4 all the way up to 1 on 97 by 99? We need to recognize is that this is just an application of this rule where n is 97. I think you would agree. Basically just doing this all the way up to the 97th term. And so what we need to do is you need to take this and substitute in 97. So 3/4 minus 1 on 2 by 97 plus 1 minus 1 on 2 by 97 plus 2 is just a number that we can evaluate as approximately 0.73985, which I think is a pretty interesting result. We can then say, yeah, we can evaluate these telescoping series like that. So yeah, it's interesting to think about, yeah, that fraction sort of converging to this value. In any case, hopefully you found that useful, and I'll talk to you soon.